All right, let's do 2.1 for IM3. We're going to talk about exponential growth. Okay, here's the thing about an exponential equation. If the variable is not in the exponent, then it is not an exponential function. So this is what we call the mother function. We could call it the parent function, but it's more fun to say mother function for an exponential equation. And the a value is always our initial value. And the b value is our base, but you might also refer to it as the rate or the rate of change. Might just be rate or rate of change. Kind of comparable to slope, but very different than a line. Okay. So a couple things in order to have an exponential growth, we have to have these two conditions, right? First condition, a can't be 0, has to be anything other than 0. And then second condition, the base b has to be a positive number other than 1, right? If it's 1, we're just going to multiply by 1 over and over again, nothing changes. So it could be a fraction, or it could be like 2 or 3 or something like that, but it can't be 1, and it can't be less than 0, so it's got to be a positive number. These are two conditions to get a exponential growth. Let's talk about these a little bit, give you some examples to play with it. So first off, is this first one exponential? Yeah, the variable's in the exponent, so yes, that's exponential. What's the a? The a would technically be 1. You can imagine there being a little 1 right out in front here. And the b is 2. Easy. How about on this one? Is this exponential? Well, the variable is in the base, not in the exponent, so the answer is no. So there is no a and there is no b in this situation. Does not apply. How about for the third one? Is it exponential? The answer is yes. It is exponential. And the a is -3, and the b would be 2.6. Why don't you take some moments to fill in these last two, see if you could figure these ones out. Okay, let's talk about the fourth one here. Is it exponential? Yes. The a is 10, and the b is actually 1/6. 1/6, but I see a 6. Why is that? Here's why. Let's play with this. What does a negative exponent actually mean? Well, a negative exponent means that you're really dividing by that. So you could think of this as 1 over 6 to the x, which is the same thing as 10 times 1/6 to the x. And now it's in the right format. And so now our b is 1/6. That's why that one's a little bit tricky. Okay, and over here you probably see that letter E and you think, oh, that's just a different variable, but it is not. The letter E is a constant. It's called Euler's number, and it is about 2.7, okay? Just like pi is about 3.14, you could say that this is about 2.7. It's just a constant with, with numbers that go on and on forever. We'll refer more to this number later. It's just a special number. That's all it is, but it is not a variable. Okay. Linear versus exponential. Well, let's think about these. So a line, right? We look at a line, looks like this, mx plus b. And it's going to look something like this, right? Where it has some change in y over change in x. That's your slope. And then it's going to have some y-intercept. But an exponential, it's going to look something like this. And what we're going to end up with is this little line right here, which we don't really graph. But this line right here, which is at y equals 0, that is what we call an asymptote. An asymptote is a graph. Well, I'll talk more about that down here. The x-axis, y equals 0, is an asymptote. Of the graph. An asymptote is an imaginary line that a graph approaches more and more forever. But here's the tragic part of it, guys. This is really sad. It gets closer, but never touches. Isn't that so sad? So I like to think of asymptotes as like this tragic love story. These two lovers, they get forever close, but they can never actually touch. Okay, then up here, I skipped this part, but basically, if it's growth, and the graph will grow away from the asymptote as you move left to right. So the reason why I say that is it's also possible. So if I had an asymptote here, right, it's growing, obviously going like that. Technically, this graph right here is still growth. It's just negative growth. And we'll play with that on the next page. So here I have some examples of exponential graphs, or are they? So are the following graphs exponential growth functions? Well, no, this first one is actually what we call exponential decay. So I'd say no, because this one gets closer and closer to the x-axis. So this is exponential decay. Yes, this is growth, but it's just negative growth. So we'd say negative exponential growth. And yes, this is our typical exponential growth. In this one, this is actually, we would call this a logarithmic growth. We'll talk more about this later on, but that's what that one is, logarithmic growth. Okay, let's talk about how we could sketch a graph of an exponential equation. So I would always start with the points 0 and 1, at least for now. When it's in this form, I'd start with the points 0 and 1, and I'll show you why. Let's put a 0 here, let's put a 1 here. And you might want to fill in a couple other points to get an idea what's going on. So maybe go a little bit before 0 and a little bit after 1, and you will probably get a really good idea of what this graph looks like. So let's talk about the domain right now. Domain is just all your x values, and there is no value that I cannot plug into x. I can plug in any number to x, and I'll get out a y. There's nothing that I can't plug in for x. So for the domain, I'm going to just say, well, this is just all real numbers. Another way you can write this is called interval notation. You can say parentheses. This means your starting value. Well, I'm starting at negative infinity, and I'm going all the way to positive infinity. And it includes all values there, right? Okay, for the range, let me say this real quick. Domain, x, range, y. Here's how I remember that, by the way. X comes before y, D comes before R in the alphabet. That's how I can always remember that very easily. Now, the range is all your y values. And to figure out your range, you kind of have to know a little bit more about the equation. And I guess you could figure it out right now, maybe, but you got to think about, as you plug in different x values, you're only going to get out a certain kind of y value. And I think when I fill in this table with you, you'll see what that is. So to fill in this table, all you're going to do, let's start with the 0. Like I said, you're just going to plug a 0 in for x. And you probably could do this in your head. If that was a 0, 2 to the 0 is 1. 1 times 1/2 is 1/2. So at 0, you get 1/2. All right, what if you plugged in a 1? Well, 2 to the 1 is just 2. 2 times 1/2, well, half of 2 is 1 again. Let's keep going. Let's plug in a 2. If I plugged in a 2 here, that'd be 2 squared. 2 squared is 4. Half of 4 is 2. What about a 3? 2 to the 3rd power is 8, and half of 8 is 4. Okay, we're getting some points here. Maybe you could even do one more. Let's say I plugged in a 4. 2 to the 4th power is 16. Half of 16 is 8. All right, we're getting some good information here. Let's do the negatives now. What if this was a -1? For this one, I'll work it out with you all over here. So I would have 1/2 times 2 to the -1. You got to think about what a negative exponent means. It means divide. So this is really like saying 1/2 times 1 divided by 2. And 1/2 times 1/2 is 1/4. All right. What about negative? Oops. I put that in the wrong spot. That's -1. There, I moved it. Now let's do -2. If I did, that'd be 1/2 times 2 to the -2. That's like saying 1/2 times 1 over 2 squared, which is really 1/4. So that's like 1/2 times 1/4, and that would be 1/8. Okay, and I don't think we need to keep going in this negative direction to see what's happening. This is just going to keep dividing by 2 or multiply by 1/2 as we go this way. It's just going to keep getting smaller and smaller and smaller. So, but will it ever get less than 0? Will it ever get to be a negative number? And the answer is no. There's nothing I could put up here in the x value. Like I could put -1,000,000, And this still won't be a negative value. It'll just be a really small value. And so that's why we could say over here safely that the range is all positive values. Or we could write it like this. We could say starting at 0, going all the way to infinity. By the way, this is not a coordinate. This is called interval notation. This is where you list your first point and your last point. And if it's infinity, it's obviously, that's as last as you could possibly get, right? You can't even really get there. Okay, with that, we could sketch a graph, okay? Let's sketch some of these points. The first points I would sketch is the 0, 1/2, which would be right about here, and then the 1, 1. And we could sketch more than this. So we also know, we learned about 2, 2, we learned about 3, 4, and we learned about 4, 8, which would get us off the charts. And all these ones are just really tiny fractions. They're just gonna get closer and closer and closer. So what we do is we just draw a nice line really close to the x-axis, and we just show that it gets farther and farther away. Put a little arrow here, and technically we have an asymptote right here, right? As you go to the left on this thing, as you go to the left, this graph will forever get closer and closer to the x-axis but never touch it. And that's, again, that's why I call it a tragic love story. Okay, let's talk about a couple things that we noticed here. So when the exponential function is in this format, you're going to always get 2 points for free. And those 2 points are, you're always going to get 0, and a is going to be 1 point. It's like your initial point. And then if you plugged in a 1, you're always going to get a times b. It'll just always work out that way. So if you know those are your like starting points, it can make the graph really easy to sketch. So for example here, on number 2, let's identify our pieces, right? We know that the a is 1/2, the b is 3. So therefore, I already know that I'm going to get a point at 0, 1/2. And at 1, I'm going to have 1/2 times 3, which is 3/2. Yeah, these are fractions, but that's okay. If I wanted to graph that, I would just put it right in the middle. And then at 1, you're 1.5. And really from here, we know that we're going to have an asymptote at y = 0. So let's just connect the dots. It's going to look something like this. Now, if I really wanted to, I could get even more points. Like I can make a t-chart like I did in this question above. But that's probably good enough to get an idea of how this thing looks. If I'm just sketching it, by the way. Oh, and what's the domain? The domain, again, is all real numbers. Remember, domain is x. Range is y. But what's the range? This is all y values. So I'm going to say it goes from 0 to infinity. By the way, these little parentheses here, they mean something. It's not just like, these are coordinates. I know it's really confusing because they look exactly the same. But when we're talking about domain or range, or we're talking about where this thing is graphed, or they say the word interval, then this is talking about interval notation, not a coordinate. So just to give you a quick little rundown what that means, to just like give you an idea. If I said a comma b and I did a bracket, what that means, that's the same thing as saying x values that are greater than or equal to a and less than b. So the bracket means that it could be equal to. The parenthesis means it cannot be equal to. So that means it cannot be equal to 0, but it's after 0. And it obviously can't be equal to infinity because that's not a real thing, but it's less than infinity. That's why we list it like that. You're going to see a lot of interval notation in upper mathematics. I just want to make sure you're familiar with what that means. All right, I'd like for you guys to try this one on your own. Identify the a and b, see if you can get figure out what the asymptote would be, and sketch it. And so go ahead and pause the video and then check back when you're ready to check your work. All right, so hopefully you play with this. You got that the a is -1, the b is 2, so you can quickly find your 2 like base points. They're really easy points to find. You could also have done a t-chart to find those. I also went ahead and found what happens when I plug in a 2. 2 squared is 4, and then you apply the negative. Exponents become before multiplying. So 2, -4, I went ahead and plotted that one as well. So I got 0, 1, 1, -2, and 2, -4. And then I just sketched the graph. We're going to have an asymptote at x = 0. Domain, all real numbers, because there's nothing that I can't plug in for x. But the range here is y values less than 0, because they're only going to be less than 0, which I could also write as from negative infinity to 0, right? From negative infinity up to 0 is what the values I'm including. And there's a quick little sketch of it. All right, let's go on to the next page. All right, so now what if we are going to shift this around a little bit, okay? You might see x minus a number up in the exponent, and you might see plus a number over here, and we call these h and k, and then this is how it's going to shift. So to graph the function above, identify the points for the graph y equals abx, so those same points, and then translate the graph horizontally, left or right by your h units, and up and units, and vertically up and down by k units. All right, that's how we're going to do this. So, give you an idea. Here's how this works, and you might want to just make sure you write this down. If you're, actually, I'll tell you what, I'm going to write it down here. So, if your mother function has your core points of 0, a and 1, ab. Here's what your translated function is going to look like. It's going to be 0 plus h, which is just h, and then it's going to be a plus k. And then if you did 1 over from there, which would be h plus 1, that's an h, then it's going to be ab plus k. And that's how we can use those core points from the mother function and just shift it over. So let's figure it all out from here. All right. If I was just doing the core points, I would have 0, a. My a is 2. Boom. And then I would have 1, a times b. 2 times 3 is 6. But I'm shifting these, right? So as I shift, I'm going to add h to 0. My h here, by the way, h is always, this is really important, h is always the opposite of how it looks. So my h right here looks like a -1, but it's not. My h is actually +1, and my k is -4. So k looks the same as how it is, but h is always the opposite. So what does that mean? Well, instead of 0, I'm going to do 0 plus h, which is 1, because my h is 1. And over here, I'm going to do a plus k. So there's my a. I'm just going to add k to it. K is -4. So 2 plus -4 is -2. So that's going to be, that's like my new core point, my translated core point. Okay, then I'm going to say h plus 1. Well, 1 plus 1 is 2. So that means at 2, I'm going to be this number, which was ab plus k. Well, 6 plus k of -4, 6 and -4 make +2. And so now I know that my core points on my translated graph are 1, -2, and 2, 2. So let's go ahead and plot those. 1, -2, and 2, 2, like that. And there's something else very important. K, I'm going to summarize this down here. Y equals K is your new asymptote. So that means I should have an asymptote right here at y equals 4. If you think about it, it makes sense. This whole thing shifted down 4 units, so instead of having it at y equals 0, it's now y equals 4. All right, well, now I got enough to make a pretty good sketch of this. That's my asymptote. It's growing this way, and it's going to kind of got a little curvy there. It should look more like that. All right, now we got a good graph. Sometimes it's easier to answer domain and range after you graph it because you have a visual for it. So here's what I would say. I would say domain, all real numbers. Or I could do it in interval notation. I could say, hey, everything from -infinity to +infinity, that's good. The range, these are going to be y values that are greater than -4. Or I could say, hey, all the values from -4 up to +infinity. That's interval notation. So that's how it works to translate a function. We'll play more with that in class, but I just wanted you to see that. These things down here, this is just some algebra review skills. You can do these if you want. Try to practice some basic things that you might need to use. There's some skills you might need to use in future problems, but you don't have to do that for these notes. There's everything on exponential growth. See you guys in the next video.